Okay, we'll get started. Looks like some of the attendees are still coming in, but we'll start making a move. So welcome everyone to this online seminar hosted by the Climate and Energy College. We've had a slight title change of today's seminar, but the topic and the speaker is the same. The title is Recent Trajectories in Urban Emissions from Remote Sensing Proxies, will be given by Professor Peter Rayner. My name is Alex Norton. I am an alumni of Melbourne University and of the Climate and Energy College. Currently, I hold a postdoc position with the NASA Jet Propulsion Lab, but in these strange times, I'm actually back in Australia working remotely, temporarily. Please join me in acknowledging the traditional owners of the various lands from which we are joining this webinar today, and in paying respects to their elders past and present. I have to mention that today's webinar is being recorded, and the video will be posted on the Climate and Energy College website. So if anyone has missed it or you'd like to look back on it later, that will become available in good time. I'll just ask for any attendees that have questions. We invite you to submit questions anytime throughout the presentation by clicking on the chat box and typing your questions in there. You can also click the raise hand button so that we can identify you easily to invite you to ask your question during the Q&A session after the talk. So today it's my pleasure to introduce our speaker, Professor Peter Rayner. Peter was in fact my PhD supervisor and continues to be a great mentor for me. Anyone who knows Peter will know that we're in for a really great talk today. Peter originally studied theoretical physics and mathematics, then had a brief foray into atmospheric dynamics before moving on to studying the carbon cycle. Today, Peter is considered a world-leading expert on the global carbon cycle. He's been a leading figure in the development of the tools that have helped us to understand where and when carbon is exchanged between the Earth's surface and the atmosphere, so-called carbon sources and sinks. In 2001, he was awarded the Priestley Medal by the Australian Meteorological and Oceanographic Society, the highest national award in his field. He's been on the science teams of a number of successful satellite missions, including GOSAT, OCO2, and more recently GeoCarb. He continues to lead the way, publishing widely in the scientific literature and supervising a growing number of students and early career researchers. Peter currently holds an Australian professorial fellowship at the University of Melbourne and is right now the acting director of the Climate and Energy College. So with that, I will pass things on to Peter.
Thanks, Alex, and welcome back. Enjoy the rest of the quarantine. Yeah, I'd like to add my acknowledgement. I'm sitting on Wurundjeri land, land that was never ceded to the Europeans, and we continue to hope for just settlement of those arrangements. I also want to acknowledge my co-authors, in particular, another graduate student, Mohammed Luqman, who has done an extraordinary piece of work to wrangle masses of data. By the time I see the data for the problems I'm looking at, it fits on an Excel spreadsheet. The kinds of data that Luqman deals with don't fit easily in the back of a truck. It's just masses and masses of data, and it's been a tremendous effort to work on. We're going to talk particularly about the kind of drivers and trajectories of urban emissions and why that might be interesting for the emission problem more broadly. So the motivation for this is kind of obvious. The human population is now predominantly urban, with about 50%. About 70% of the emissions or energy consumption is kind of associated with urban areas, that already tells you that urban dwellers contribute disproportionately to fossil fuel emissions. And the urban regions are growing very fast. So it's kind of important to know what that's going to contribute to the growth in fossil fuel emissions, particularly of CO2. And there's two kind of narratives that play out around this story. One is a rather gloomy narrative that imagines people being sucked into growing cities from kind of low impact, semi-agricultural or rural kinds of lifestyles, with them getting wealthier, which is good, but also driving up emissions and energy consumption as the cities swell and swell with these arrivals. And the other is that, yes, that's true, but you can't project that forward because there's a stage in a city's development where the modes of economic production change and the cities become essentially relatively green engines of growth. And one can find examples of either of these around the world. And what we were trying to do was to really make a global survey and see which of those narratives was dominant globally and what that might tell us about what's happening for the future. And on the way, we kind of generated a data set that might be interesting for a range of other applications around cities, and we'll discuss that as we go through. Here's an outline of what I'm going to talk about. I'm going to talk about what we're doing and particularly what we're not doing, because this is a rather contentious area. I'm going to spend a bit of time talking fairly quickly, but walk you through how one determines the boundary of a city. This turns out to be a ridiculously hard problem, and trying to do this consistently. I'm then going to describe a fairly simple decomposition of emissions in cities that is a way of us thinking about the contributions to the trends, and it's borrowed from some work that people did a decade or so ago on national emissions. Try and find some patterns for these drivers for cities and see if we can understand kind of whether there are forms of development for these trends. And then I want to compare urban emissions and the emissions of their host countries, because that's kind of the critical question here. Are cities more or less growing more or less proportionately to their national emissions? And I'll speculate a little bit on what that might tell us about trajectories. I say we're looking for global patterns in emission trends, and the problem with doing this is that cities are ridiculously diverse, of course, despite some kind of very brave statements about the only thing that matters about a city is its size. That's clearly not true. The only thing more diverse, perhaps, than cities is the kind of data sources that one has about them. Cities are reported and catalogued and described in a whole range of different ways by a whole range of different people. So finding global and consistent data sets on cities is extremely hard, let alone the problem of finding out how big a city actually is. What does it mean to describe the size of a city? And finally, we need data that's long enough that we can actually talk about trends. It's hard work to get a snapshot of a city, let alone to get a description of a trend. So what are we not doing? Well, first, maybe an apology, I'm not quite sure. We are looking for a series of fairly simple, compact explanations of how cities are developing, simple kind of descriptive forms. And that's a kind of essentially reductionist project. We're trying to find relatively simple descriptions. But we're not looking for universal laws. We're investigating the data rather than trying to find underlying rules. And at the moment, we're not really looking at the underlying drivers, why cities developed in this way, but really trying to find patterns. So any prediction that we make is not really based on an underlying mechanism for how cities develop, because there probably isn't one, but is really a comment about a business as usual scenario. And we'll find that, in fact, it's going to be quite hard for us to derive those scenarios. So how on earth might we do this? You can probably guess that any approach that we use is going to be quite dependent on global data sets. It's not that there isn't better data than on cities around locally. There's much better data on individual cities, probably on any given city, but it's inconsistent. So trying to find patterns globally on what's happening by looking at diverse data sets won't work. With luck, the approach should be algorithmic, or at least nearly so, and that's partly because it's make it feasible for humans to do, but also that there's some chance of consistency from point to point. It shouldn't rely on local data provision, because the chance of us getting local data for a range of cities around the world is very small. And so this really limits us to, at the moment, to remote sensing products. Until there are good reporting structures around for how cities are behaving, we're forced to kind of look down on them from above. So what do we actually do? We're going to look at a series of satellite products that might enable us to define reasonably high resolution boundaries of cities annually. And the obvious knowledge of the boundary isn't firm, it's not a hard boundary, but that can at least allow us to make some comments on the change of city size. And we're going to impose those boundaries on high resolution maps of population and emissions, and essentially integrate over some sort of polygon that we define as the city, generate time series of populations and emissions and whatever else we can get that will describe how the city is functioning, and use those to analyze trends. So the first task is to determine urban boundaries and their trends. And this is the result, a reference there to the first paper from Mohammed Luqman's PhD, and a website that describes an algorithm and some data that we're gradually putting together of cities. So how do you define a city? Well, there's lots of ways you can do this. You can define it economically by kind of spatially connected activity. You can define it geospatially by some sort of contiguous built-up area. You can define it in terms of connectedness by looking at road networks. These will all look pretty different and are probably all individually unreliable. So what we've done is essentially to combine three of these: a measure of surface type, a measure of contiguous economic areas by looking at nighttime lights, and a measure of connectedness by looking at a road network. And anything we do with this combination is going to generate boundaries that are kind of arbitrary. Most cities don't have firm boundaries, they kind of tail off. But hopefully, the trends we get in the changes of sizes will be meaningful. So the process is a three-step process. We're essentially going to combine three measures and then use a kind of decision rule to say, is this pixel part of a city or not? So we're going to combine, as I said, things on surface types, on night lights, and on the road network. Let's have a look at each of these individually. We're going to look at a case study here, which is Brisbane, because it turns out to be a slightly interesting case for demonstrating some of the problems with this. This is a composite Landsat image made from 30-meter imagery that's now available thanks to the generosity of I think, the USGS that's made this data available for a long time. It's masses of data, even for a single city. There are a lot of images that you need to work through to try and get a picture even for a single year. And this is what Luqman has done for a couple of decades. So here's one for Brisbane. This is in 2018. What do we do with it? Our basic task is to look at that previous image and say, is a pixel here urban or not? So what we basically do is to take an existing reliable lower resolution categorization that's taken by the MODIS from the MODIS satellite, and train our data set against those MODIS classifications, and then apply them pixel by pixel across this enormous data set, even for a single city. For the details, we actually use a random forest algorithm that's implemented on the Google Earth engine to glare at these pixels and look at their spectral signatures and the like. There's a pretty standard classification method that one uses, 16 classes of surface types, forests, crops, bare soils, built up, et cetera, et cetera. We pass via these 16 classes, but eventually we want to get down to 2 classes. Is it urban or is it not? And if it's urban, we give it a score of 1. If it's not urban, we give it a score of 0. One extra wrinkle that we need to deal with is the fact that cities have holes in them. There's quite a large park not very far from where I'm sitting, and we want that included in the city. We want really an envelope polygon around the city. So we apply some kind of neighborhood smoothing to make sure that we don't get fooled by gaps in a city. Can we test it? Well, it's hard, but one of the ways we can test it against training data sets is what's called a confusion matrix, which essentially tells you, it's kind of a table that tells you how much of a true class is classified correctly and how much is splattered into each of the other classes. So if you have 16 classes, this would originally be a 16 by 16 matrix. And in our case, on the 16 class classification, we get about 75% correct. And on the 2 class classification, when we come down to look at just urban or not urban, it's over 90% and generally quite a bit over. Is that good enough for boundaries? We think so. We think the areas will be consistent and kind of not alias into changes in the boundary, but there's work to do there. So that's the surface. Here's a different view of Brisbane. This is a nightlight image. And again, I think the nightlight image is on, if I remember, the left, and the classification is on the right. And again, this, as I said, is for Brisbane. These nightlight images have been kind of famous from space. They make spectacular pictures. NASA loves taking these from things like the International Space Station. These ones are not taken from that. They're taken from a couple of long-running programs, initially from defense satellites that were looking for clouds, but looking at angles that enabled them to see nighttime lights in cities. And after that, for a range of satellites looking that are involved in weather and surface activities. They've been pretty widely used as proxies for various kinds of human activity: settlement density, population, economic activity, fossil fuel emissions. There's a few papers that I've been involved in over the years that have tried to estimate fossil fuel, gridded data sets based on these nightlights, and we'll actually use that again. It's approximately, I think I've said 2 kilometers resolution. It's actually about a 1 kilometer resolution, available since about 1990. No, it's 2 kilometers available since 1992, and about 700 meters resolution since 2012 as we had a change of instrument. And that's a nice long data set. Again, it's not spectacularly high quality. The scale of the measurements is just 0 to 63. That's not much dynamic range. Nightlights actually vary over much broader ranges than that. The new measurement, VIIRS, available since 2012, avoids a fair bit of that problem, has a much higher dynamic range. But that 0 to 63 is probably enough for us to classify a spot as, yes, this is continuously lighted, it looks like it's part of a city, or no, it's not. We essentially assign a threshold. We assign the threshold at 45. Again, we tested that a little bit against some direct imagery, and just like for the surface classification, we assign this a score of 1 if it looks above 45 and we call that urban. Otherwise, we give it a score of 0. Finally, travel time. And here we see essentially contours of travel time, or a color map showing travel time to the center of Brisbane. And this is based on OpenStreetMap, where essentially we generate measurements of shortest path, road length, from a given point to the center of the city. So, yeah, analyze road length, as I said. Assume some travel speed. It doesn't particularly matter what we assume. It's probably a bit, of course, it's more complicated than that indeed. There are different kinds of roads that allow different kinds of travel speeds, but they don't change much from year to year. So they probably won't affect trends in the boundaries very directly. So once again, we assign this a score, which is a little more complicated. If we calculate the travel time in minutes, we assign it a score of 10 divided by the travel time. So the smaller the travel time, the higher the score. We break this up into series of 10 minutes, contours of 10 minutes. but essentially, the closer you are to the core, the more likely you are to be considered urban, which seems perfectly fair enough. How do we combine these? Essentially, we add scores. So we kind of have this decision rule that we add the 3 scores together and we assign a threshold of 1.5. Now, if you're kind of across what that means for the impacts of the 3 different contributions to the boundaries, you'll know that if both the built-up area and the nighttime lights agree that it's a city, it doesn't matter what the travel time is. If they disagree, or if they agree it's not a city, again, it doesn't matter what the travel time is. The travel time really helps us with the case in between, where one of them thinks it's a city, the other one doesn't, and the travel time can tell us whether we think it's well enough connected to the center. How on earth do we test this? It's really hard to do. And the main reason for that is very few other data sets have the right kind of form. If we're interested in seeing whether our trends are any good, there aren't many others of these data sets that have been done beyond a snapshot. There are many other urban extent data sets, but they've generally been taken for a year, or maybe 2 years, 10 years apart, or something like that. But we've had a look at a few tests against snapshots, first to see how our boundaries go, and also to see whether we're making kind of consistent errors for any data sets that do have multiple years. And in general, the growth rates we're predicting are reasonably close, but there is a pretty broad scatter in what these growth rates look like. And perhaps that's not surprising when the definition of a city boundary is functional. Cities will grow different ways at different times. One more curious problem here that we ran into as we looked through this is what's called the fusion problem, where cities generally grow kind of gradually. They're putting on stuff around the boundaries and putting on stuff around the boundaries, and then occasionally, according to the imagery, they appear to, in this case, grow a tail, where I think in this series of images at about 2013, Brisbane appeared to grow a tail. So what happened, essentially, Brisbane fused with the Gold Coast, according to this imagery, at least. And that's a relatively common phenomenon. And Beijing, for example, since I think the last 10 or 12 years, has fused with about 13 surrounding areas that would have been regarded as cities in their own right. Now, that makes our analysis fairly difficult if we're trying to understand trends that look like really big trends in area, when in fact they're probably not meaningful for the kinds of numbers we need. So we kind of remove cities that show these crazy 20% growth rates in a year. That's almost certainly fusion, and we get rid of it. So what are we left with? Here's the location of the cities that we've got for the analysis we're going to do from here on. There's 109 of them. There were initially about 130, and 20 of them were rejected either because we didn't have enough data or because the fusion problem meant that their growth rates were too hard to work with. They're responsible for about 40% of urban emissions. Now, that's probably not enough for us to make comments on an exact trend in urban emissions, but it's probably enough of a survey data set for us to understand what cities are doing more broadly. There's an awful lot of these in China, I think 23 of them. There's about 26 in North America. I think I said the US there, but I think a couple of those are Canada. And so any analysis that we do, because we've picked large cities, we wanted to try and capture as much of the emission spread as we could, as efficiently as we could. That data set is necessarily going to be biased towards the places that have large cities. So the more we can sort of look down this spectrum of cities, the more reliable the comments we can make. But we've got 40% of the emissions. That is probably enough for us to start to make comments on patterns. Let's now have a look at the data sets that we're actually going to work with to make our emissions estimates. Here's one of them. This is from a paper in 2018 that's quite frequently updated, and it's an estimate of high resolution fossil fuel emissions, partly using those night lights that I mentioned earlier, and using a range of other things too, a series of fairly simple models some data available on large point sources like power plants, and national emissions. So we essentially use our measures of economic activity like night lights to say how much of the national emissions lives in this pixel rather than that pixel. And so it's a data set available at the resolution we're going to use, effectively 1 kilometer or 30 arc seconds, to map our city emissions and then sum over them to produce our integrated emissions. As I said, it suits what we need. It's a 1 kilometer spatial resolution and 1 year resolution. For those of you that are across the fossil fuel problem, you might be surprised I'm not using a product that I'm more closely associated with, and that's just because we don't have it, the so-called FFDAS, Fossil Fuel Data Assimilation System product, which I think is perhaps a little more mechanistically based than this product, but at the moment we don't have it at that 1 kilometer resolution. That's kind of our next task. For population, here's a picture of the Landscan dataset. This is kind of the standard large dataset that people use for gridding population, again, at the same kind of resolution. It uses a large suite of datasets and essentially trains them on cities where it knows the population and hopes that that training can extend to the rest. So again, it uses night lights because they're so convenient for working out where lots of dwellings are. It uses census. It uses again, things like road density, some measures of building density if you can get it, and so on. And once again, it suits us here. It has this 1 kilometer and yearly resolution so that we can, again, look at trends the same way as we can for emissions. So just to show how that works together, we've actually picked a single emissions and population image and drawn a series of boundaries on it for different years. That's not quite what we do, of course, because one of the things we're interested in knowing about is the fact that not just the boundaries change, but the structure and the intensity of these emissions also change. So we won't be doing it quite this way, but we will try and separate the role played by the enlargement of the city from the role played by the intensification and the change in structure of the emissions. So, yep, here's how we calculate the city totals. We essentially define this envelope polygon for the city, sum over it, and that will generate for each city a number for each year, either population or emissions, or actually anything else that you care about. If there are other things you want to look in for geospatial estimates on cities, this algorithm is now available, and a whole range of cities have been processed where we can look at the spread of any given property over a city. What's going on here? Okay, so now finally some results. Here's a first picture of emission trends in cities, and we didn't quite do this in cities because it's quite hard to look at countries like China and the US with their 23 different cities. So we averaged the city growth rates across a country. So this is the emissions growth rate, and it's in relative terms, so it's a percentage growth rate, essentially the trend divided by the mean. And we see the kinds of patterns we expect. We see high growth in developing countries, lower growth in developed countries, with a few interesting exceptions. Australia and the US both stand out for having higher growth rates in their cities than most other developed countries. Curious, we'll get back to why that might be down the line. And there are also some other countries that are showing probably some anomalous results, that these data sets are difficult. So some of these data sets, individual cities are not something I'd be commenting on in too much detail. So how do we decompose these? And so here I'm going to follow some analysis that was first done, to my knowledge, by Michael Raupak about 10 years ago for countries, where essentially you can look at the individual components that contribute to a trend. And the way you do that is essentially if a property, like the emissions from a city, can be written as a product, which it can here. It can be written as a product of the area times the population density times the emissions per head. Now that statement's true. It's like saying that A equals A over B times B. So there's kind of no problem with the mathematics there. Whether it's applicable and whether we're actually measuring what we need is something we'll get back to. But once you've got that identity in front of you, you can then differentiate it with a bit of high school calculus and divide by the mean, and you get eventually the interesting and useful expression that the relative trend, the percentage trend, if you like, in these quantities is the sum of the percentage trends in each of the bits. So you can look at the percentage growth in the overall emissions as the percentage growth in the area, the percentage growth in the population density, and the percentage growth in the per capita emissions. And that gives us a chance of looking at some of the underlying drivers for these things. And the way we've done it here is to look for patterns, look for clusters of points. So we've defined out each of our cities by these three variables. We have a kind of three-dimensional space with 109 points scattered around it. And we want to see if there are clusters. So, and this is a pretty standard cluster analysis where a cluster is defined as a group of points that are closer to a center than they are to any other center. And that's been a standard technique in statistics forever. And the center is kind of defined as the average of the points in our cluster. And as I said, in our case, it's 3D. We have these area growth, the population density growth, and the emissions per head, the per capita emissions growth. There's always a question in cluster analysis, how many clusters do we need? So we ran the analysis from one cluster, which is the whole thing, up to, I think, 11 or 12, and graphed it. And you generally pick a point where after that, you don't gain too much more or too much more rapidly. So this is kind of a different version of flattening the curve. We're looking for an elbow in our curve here. Looking at this graph where we see that the kind of mean square or the mean distance drops from kind of 4, and the units for this are percent, remember, down to about 1 or something like that. But there's an elbow in the curve at about either 3 clusters or at 5 clusters, and we've chosen to use 5. So now we get maps of what our clusters look like. So there are 5 maps here that show the spatial distribution of the 5 different clusters. So not quite sure how easy it's going to be to flick backwards and forwards between these figures, but essentially there are 5 clusters here, and 2 of them, clusters A and D, are kind of moderate growth. B and C are crazy. They have really high numbers for one of the values. The cluster B, if I remember, is growing its area by sort of 8% per year, which is a city that's in danger of eating the world or something like that if it goes on for too long. And cluster E, I just don't believe. There are 2 cities in it. I suspect there's just noise. It's 1 city in China, 1 city in Angola. They were so weird that they got their own cluster because no one else wanted to talk to them. And I think it's probably just noise in the data. So I'm not going to pay too much attention to cluster E. The clusters do have some things in common. In general, P is negative. That says that the population density in cities is generally going down overall. Cities are generally thinning in terms of their populations. Per capita emission growth negative is relatively rare. It happens, but I think cluster D is the main one that has this kind of green looking, if you like, development. Should have used the color green for it. That shows that the per capita emissions in that city are actually going down. The other thing we can look at is, are there relationships among these trends? Now, this is a hard, so what we've done here is we've got 109 points, and so we can calculate things like correlations and regressions and anything else that we feel like between these trends to see whether if a city cities in a country, because we probably average across the country, but if, in our case, if a city is thinning more or less rapidly than the average, does that mean that per capita emissions are going up or down faster than the average? It's not a causal relationship that says if you thin a city, that emissions are going to go up or down, but it is a comment on the patterns with which cities develop. And the one that we see, which I think is most interesting, is a reasonably significant negative correlation between P and E. So it does in fact tell you that as population density, or as a cities thin more rapidly, so P is more negative, so in relative terms, their per capita emissions go up more rapidly. So that's a comment which, if we can find an underlying driver for that, and one can imagine things like transport might be involved, that would be a really strong commentary that the kinds of roles of urban densification and so on that we see are a global phenomenon. It's a globally important shift for controlling the emissions of cities, is to do something about population density. And finally, to compare urban and national trends. So this brings us to our fundamental question: does urbanization increase emissions? So the way we can think about this is, if cities just go on sucking in population, but their per capita emissions don't change, then urbanization itself is not making a particular change. So what's key here is the relationship between urban emissions and the country as a whole. So we took data from the IPCC, looking at effectively the fossil fuel emissions for a country, used Landscan for the population, and then did the same thing for our cities in a given country. And here we generated a map of where the cities are, we call them fast or slow. And I've only learned quite recently, we got the colors backwards. So I think the countries I've listed here as red, and I think are labeled as fast growth, should actually be labeled as slow, because they're cities in which the per capita emissions in the city is growing slower than it is in the country as a whole. And if cities are going to play a benign role in driving fossil fuel emissions, that's what you want. And the hope is we might see some trends. And in fact, it's a really mixed picture. It would be hard pressed to find clear patterns about whether cities are fast or slow across that diagram. It's quite different from the patterns of overall emissions that we saw earlier. There are a couple of cases that are clear. China, well, it's clearly red. It's red in our case here. It should be green. It should be a slow cities. Our expectation is that is not necessarily a greening of the development of a city so much as a clearing of a range of industries, probably largely for air quality reasons. So that is a result of a different policy rather than a climate outcome, we think. India is also pretty clear. If you actually go back and look at the numbers, India has a very high growth rate in its urban emissions compared to its national emissions. Could we find drivers for this? And the summary answer is no. So we were hoping that we might see things like urban minus national emissions changing with GDP. That goes back to this narrative that beyond a certain level of development, cities start to grow green. So going back to that map on the previous slide, you probably see that there's not an obvious relationship between whether you're in a rich part of the world or a poor part of the world, or recently developed or longer term, that kind of thing. So kind of glared at the data in various different ways, ask questions like, if I'm a rich country versus a poor country, so am I above or below the median per capita GDP, does that predict with any power whether I'll have fast cities or slow cities? And it doesn't. There is a weak negative correlation between GDP and the difference between urban and national emissions. And who knows, if we crunch down several hundred more cities, that relationship may strengthen, but at the moment, it's not enough to base a strong kind of evidence claim on. a couple of interesting comments there are that one of the reasons this correlation is relatively weak, or this relationship is relatively weak, are a few countries. So Australia and the US that have very high per capita income, some of the highest in the world, and I think the highest in this data set, have fast cities, which is not what, in general, what we expect to see from this development narrative. And similarly, China, which is sitting just below the median, so it's sitting in the, if you like, in the poor half of the per capita GDP, has slow cities. So if you remove them, the relationship does indeed get a bit stronger, but it's still not strong enough to kind of base a strong claim for evidence on. So in answer to our question about the narratives, I think it's pretty clear that both narratives are in play, and we're now looking for kind of other descriptors of cities to see whether there's something else that can tell us whether a city is going to be relatively fast or relatively slow compared to its country. And that might be things like urban form, it might be some piece of historical information that we can learn about the city, but at the moment, that pattern's not obvious. A whole series of caveats here. You probably noticed how many times I've mentioned the nightlights data set through this talk, and it kind of pops up. It's such a convenient proxy for things to do with human settlements that it turns up all over the place. So one has to be at least watchful of the independence of the underlying data set. Now, there's a few things that we've tested the robustness of about this. Are things like the relationships between the growth in population density, or the change in population density, and the change in per capita emissions. Is that very sensitive to the description of the area that we have, the boundary that we have? And it turns out it's not. But there's still a range of other concerns that we might have about how just independent these 3 points that we're talking about really are. More fundamentally, what is it that we're talking about when we use this decomposition of F equals APE? Is it energy consumption or emissions? So what kind of combination of scope 1 and scope 2 is it actually? And that's not entirely clear. We know that at certain spatial scales, that fossil fuel flux based on nightlights is a fairly good proxy for emissions. That's been tested against direct data sets. It breaks down as you get to finer and finer resolutions, and where do we sit in that kind of breakdown is an open question. So there are concerns about what it is we're actually measuring. There's a point at which that doesn't matter too much, whether it's energy consumption or actual emissions. The energy consumption has to come from somewhere, unless the economy is greening overall, which is to do with the decarbonisation of the energy system. Then energy consumption is still an important thing to know. And the final comment is just one on noise, that when we calculate a per capita measurement, we're effectively dividing something, be it a total emission or a total population, a total emission or something else by population. Both those data sets have noise in them. So it's not surprising, perhaps, that some of these cities behave oddly. Things we wish we had, more cities, already talked about that. We are wondering whether some of these relationships would come out clearer if we had more cities. We would love a gridded GDP data set. But unfortunately, again, we'd prefer it to be independent of nightlights. So finding something that can downscale measures of economic activity to the kinds of scales that we're looking at, so we can actually measure changes in from year to year, looks really hard. We'd also like more sectoral information. So we'd like to know whether this relationship between population density and per capita emissions looks like transport, because that's an obvious mechanism for it to happen. Conclusions. Urban emissions are growing, it's no surprise, but the patterns look quite complicated. The differences between developed and developing countries and the different patterns that we see have been driven by the area increase versus the per capita emissions increase that we see showing really these quite broad scale consistent patterns, largely to do with development status, but probably other things to do with urban form that we just haven't kind of teased out yet. there is an intriguing negative correlation between population density and per capita emissions, and what is that telling us about urban form again? And the evidence for the relationship between urban and national emissions changing with the development status of a country looks really tough. It looks as if there's just not a kind of obvious hit you over the head message about how that relationship looks. And here's some acknowledgements. So it's actually, I've already commented on the effort, particularly that Luqman's put in. I also just want to thank in general, something that we kind of take for granted now, but I'm old enough to remember when we couldn't do that, which is that the open source and data movement that's made these masses of really expensive data available to us as researchers free and in a reasonably well curated form. This research not only wouldn't have been technically possible 20 years ago, but it wouldn't have been bureaucratically possible. We just could not have afforded access to the kinds of data that we had. I also want to thank or acknowledge the Google Earth engine, which was the platform where Luqman crunched these masses and masses of Landsat images to generate the urban boundaries. All right, I'll stop there.
Okay, fantastic. Thank you so much, Peter. Really great presentation and bringing big data to some important questions on how our cities are growing. So I will start going through some of the questions in the chat now. So I will pick out each of you who have posted the questions, and I will allow or activate your ability to speak. I will try to anyway. So we'll start off with Lee White. And Lee, if you'd like to just briefly introduce yourself, and you can pose your question.
Hi, I hope the microphone is working.
Yep.
I'm Lee White. I'm a researcher at the Australian National University. One of the things I study is city level policies to reduce emissions. So this is something that was very interesting as would this data set be a way to see how effective the city level policies were? But something in the emissions accounting that I was wondering about was a lot of the things that are targeted by the city policies, for example, transport use or trying to increase building efficiency, don't seem like they would be showing up in the way that the emissions are aggregated when it's the national level sort of portioned out. And I was wondering if there was anything addressing that within the data collection.
So part of the problem here is that policies perfectly rationally target sectors. They target sectors of the emissions, and you pointed out two there, building emissions and transport emissions. And we would just love to have sectoral information at these kind of scales globally to enable us to try and drill down, if you like, into can we see sectoral differences in the way some of these cities are developing. That's actually, I should have added a future work slide here, but I mentioned that we're pushing ahead with the development of our own high resolution fossil fuel product. And the hope is that that will be sectorally detailed enough to look at exactly that point. Some of this will be easy, or at least conceptually easy. We should be able to see things like changes in transport, and that'll be looking at a range of other pollutants that measure transport activity, plus whatever data we've got from globally available transport counts and so on. Some of it will be really hard. How building emissions change is one of these things that it's a nasty mixture of modeling and data. So it's going to be pretty hard for us to look at that. We'd love to. And if we can, I'd very happily chat offline to see if you can think of proxies that might help us describe that. So, yep, I agree completely that it's hard for us to see the targets of individual policies. We can probably get some sense for aggregate policy impacts. It might be interesting for you to classify, okay, cities in this part of the world or in this country have strong policies. These have weak policies, these have none. Does this help as a descriptor for some of these patterns that we're seeing, for example, in per capita emissions? But getting down to detailed sectors, yep, possible for some, probably really hard for others.
Thank you. Sounds like an interesting future data set potentially.
Okay, next up, we'll go to Roger Dargaville. Let me unmute you, Roger.
Thanks, Alex.
Take it away.
My internet connection's a bit dodgy at the moment, so I hope I'm coming through okay. Peter, this is a fairly pedantic little point, but you mentioned population thinning. And I just wanted to clarify that that's what I think it means, is that the city is growing in such a way that you're getting more low density growth on the fringes relative to the high density growth in the middle of a city, for example. Not that you're actually seeing less high density living in middles of cities.
I suspect that's true, although we haven't looked at it. So we've not gone to the extra step of decomposing the structure of populations within the city to say, are we putting on this kind of umbra of low population urban sprawl around the edge versus kind of flight from the high density inner parts of cities, whether that's explaining it or whether in fact it's just an overall growth. We've just looked at numbers in aggregate. It would be really interesting for us to see if we could actually tell which of those was happening. I suspect that in most cases, just looking at the area growth rates that we're seeing, that in fact, what's happening is that cities are probably densifying within most fixed boundaries, but they're growing rapidly enough that the overall impact is a thinning.
Yep. Okay, thank you.
Thanks, Roger. Next up, we'll go to Stephen Pollard. Steve?
Yeah, hello. Thanks, Peter. Thanks to your whole research team for this really interesting work. I'm a PhD student at the Climate Energy College, a social scientist, and also interested in boundaries, how boundaries are defined around local targets for community scale carbon neutrality. But my question was about how you deal with emissions, sort of scopes of emissions, and you've touched on it a little. But how do you deal with emissions from energy consumed in a city that's generated elsewhere, such as scope 2 emissions from stationary energy, or even with emissions from, say, manufacturing a product in one city that's then used in another city or even in another country? And do these emission scopes, even really matter so much at the global scale of analysis that you've undertaken?
So I think the two examples you quoted are beautiful because they point out an important difference. I think the first one probably doesn't matter. From the point of view of the overall energy demand of a city, if we think that people are going to produce energy to meet the demands of humans, there are questions about how they meet that demand, but the question is whether the emission is actually happening in the city or it's happening outside. Doesn't matter so much for this question. For my day job of looking at atmospheric measurements that might tell us whether these emissions are happening where we think they are, it's absolutely critical to know where they happen. But in some sense, the scope 1 versus scope 2 question about whether we're seeing energy consumption that's driving emissions elsewhere or actual emissions in the city is probably not so critical for this analysis. The other one, the question of embedded emissions, is absolutely critical. And we haven't addressed that problem even slightly. So this question of to what extent we are effectively outsourcing emissions for whatever reason, our own, that's essentially to do with arbitrage of costs or to do with clean air policies or whatever, is something that we just haven't addressed. It's a speculation, but I think given the strength of the Chinese air quality policy, it seems quite likely to me that some of what we appear to be seeing in the cleaning of Chinese cities has to do with effectively moving various emission sources outside urban boundaries rather than a reduction in overall emissions, and that's going to significantly bias this difference between urban and national emissions. But the other question of, yeah, we're using lots of products, they use energy, if the energy is used elsewhere, they don't turn up in your night lights, but they're sure as hell demanding energy from somewhere is an absolutely critical question, but it's not one that the kind of analysis we're doing here, which is static, can deal with very easily.
Great, thank you. Thanks, Peter.
Okay, we've got a few minutes left. Maybe have time for one more quick question. So, Craig Burton.
Hi there. Thank you for this presentation, Peter. I'm Craig Burton from the Global Building Performance Network, which is an NGO, but it's based at Monash University. We are looking at the outcomes of policy changes, in particular building code changes in places like India, Indonesia, Malaysia. So this work is really, really, really interesting. We have some data about the effect of policies countrywide. We started off in Europe, it's a French NGO, but we'd really like to follow what you're doing because being able to quantify the eventual outcomes from changed building codes, this is the sort of the ultimate outcome of our work if we could determine that.
Yep, let's talk. That's kind of what we'd hope to be able to do. I think you might find that you're answering as many of our questions as we are of yours, right? Because you probably have some, it's clear now that the patterns that we're going to look for are going to be patterns that are driven by something that's not immediately obvious from just the development status. So it's probably something to do with policy or form or something like that. So each time somebody comes back to us and says, yes, we'd love to know what the outcome of some policy setting is going to be, we'll immediately respond with, we'd love to know what the spatial distribution or form or temporal change or onset date or anything of a change in policy setting to see if we can actually see it in the emission changes.
Okay,
But
I might.
Sounds like a really productive conversation.
Yep, I might chase you up later. Thank you.
Okay, we'll leave it there. Thanks again to Peter, and thanks everyone for attending today's seminar. Just a reminder that there will be another seminar as part of the Climate College series next week, titled Shaping the Grid of the Future, Perspectives from California, given by Alison Ong at the University of Melbourne. And you can see the details there on the screen. So yeah, thanks again to everyone that attended, and we'll see you next time.